So last time we talked about something called Newton's method, which was a way to approximate the zeros of a function using derivatives. And today we're going to talk about something called differentials, which uses derivatives again to approximate function values or the error in measuring something, anything like that. So differentials are basically, it's just a fancy word for a rearranged derivative. So we have two different things that we talk about when we deal with differentials. We have something called delta y, and delta in math, which the delta is this little triangle symbol. The delta always stands for a change in. So the change in y is or change in anything is always your final minus your initial value. And when we're talking about the change in y, we're talking about some function value at a larger x value minus the function value at the smaller x value. So this delta x is just your change in x. So this is an important formula for you to know because it definitely helps you to approximate function values with differentials and anything like that. And that delta y is going to come up in a lot of problems. Now, as delta x approaches 0, so as we let delta x get smaller and smaller, and as it goes to some infinitesimally small value, we get this dy instead. So dy is the differential of y. And this is what brings into play our derivative. So dy is always just f prime of x times dx. Now you might be saying, how am I supposed to remember that formula? Well, from all of the derivatives we've been taking, you know that dy over dx is just another way to write f prime of x. So now if we rearrange this equation to solve for dy by multiplying both sides by dx, to isolate the dy by itself, the dx's are going to cancel over here, and we're simply going to get that differential of y formula. And as that delta x goes to 0, your dy, your delta y and your dy are going to approximately equal each other. So in other words, as you let your change in x get smaller and smaller and smaller, eventually your delta y and your dy are going to be about the same value, which is how they're connected to each other. So we talk about delta y when we're talking about a difference in x, that delta x, that's a larger number, like maybe it's 1 or 0.5, 0.1, even 0.01. That would all technically be a delta x. Whereas we talk about dy when we're talking about your dx's being basically 0. So whenever you're doing a problem and they tell you that, say, like dx equals 0.1, that's really a delta x because a dx should really be an infinitesimally small number. So that's just something to keep in mind. So let's figure out how to use these differentials, or at least how to find a differential. So like I just showed you, the differential formula comes from just rearranging the derivative. So for this function, for y equaling sine of 3x, in order to find your dy, what you want to do first is you want to find dy dx. So in order to do that, we're just going to take the derivative of sine of 3x. So what we're going to do is we're going to use our chain rule because we have the sine and a 3x inside of it. So the derivative of the sine of 3x is just going to be the cosine of 3x times the derivative of the inside, so we're going to get 3. So now if we multiply both sides by dx to cancel it over here on the left-hand side, we're going to get that dy, or our differential, is equal to 3 cosine of 3x dx. So that's all you have to do in order to find a differential, is you just take the derivative and multiply your dx to the other side. It's going to work the same way for every single problem. Okay, so now we want to use a differential to approximate a function value. So whenever we do that, if you remember from the first slide, we knew that the delta of y was equal to f of x plus delta x minus f of x. So when we want to approximate a function value, so it could be something like approximating the square root of, say it's 5. So we don't know exactly what the square root of 5 is, but we do know what the square root of 4 is. So we could use the square root of 4 in order to approximate the square root of 5. So in other words, we would want to be solving this equation for this value. So if we solve for f of x plus delta x, all we have to do is move that f of x over, so we get f of x plus delta y, which is exactly this first piece of the equation that's written on your screen. So when we're trying to approximate this value right here, f of x plus delta x, we're first going to say, well, that's just equal to f of x plus some change in y. But the change in y, that delta of y, is approximately this thing. Because delta y is approximately dy, and we've already learned that delta of y is just your derivative multiplied by dx. So it's approximately going to be your derivative multiplied by your delta of x, which is where this thing is coming into play. So this is another important formula to know, is that when we try to find the function value at some x plus delta x, we're really just going to take the function value at x, not equals, whoops, and add the derivative of that value multiplied by your delta x. And your delta x is always just going to be the distance between this x value and this x value. So let's put that into action. Let's see how that works. So we're going to use differentials to approximate the square root of 16.5. Now the first step in this is always to figure out what function you're using. So since we want to approximate the square root of a number, we're going to let our function, or y, be equal to the square root of x. So then our second step, so our first step then was to find the function. Our second step is to find our differential. So we're going to find dy dx first. So we could rewrite this as x to the 1/2 power. And then we know by the power rule that that's just 1/2 x to the negative 1/2 power. And then to find our full differential, all you do is multiply that dx over. So if we rewrite this, we're going to get 1 over 2 square root of x dx. So that's all it is. So now we have our differential. So the next step is to figure out what x and delta x are. So since we want to find the square root of 16.5, we're really trying to evaluate f of 16.5, because we would have to plug that x value and we'd get exactly what we're trying to approximate back. So we don't know what the square root of 16.5 is, but we do know what the square root of 16 is, and that's the closest perfect square to 16, so we want to use that. So we're going to let x equal 16. So x plus delta x is supposed to equal 16.5. So that means that if we know x is 16, now all we have to do is solve for our delta x. So in this case, it's really easy to see that delta x is just going to equal 0.5. Now, just take note that if we were trying to approximate 15.5, so say we still let x be 16, but now we were trying to approximate the square root of 15.5, if we plugged in for the 16 and then solved for that delta x, notice that your delta x would then be negative 0.5. So your delta x, your change in x, can be negative. So your delta x is going to be a positive value when the number you're trying to approximate is larger than the x value you pick. But it's going to be negative, like it is over here, when your x plus delta x is smaller than your x. So that's just something to keep in mind, because sometimes in the problems you will have a negative delta x, and it'll change, whoops, what your final answer will be if you plug in with the wrong delta x value. You'll get, your approximation will be further away than if you had the correct delta x value. So now that we have our x and our delta x, we can set up our approximation formula. So we know that f of 16.5, we can just rewrite that as f of 16 plus 0.5, which is going to be approximately equal to f of x plus f prime of x times delta x. That's just our general formula. So it's going to be approximately equal to f of 16 plus f prime of 16 times 0.5, which I'm going to write as a half just to make our computations a little easier. So if we remember, we had f of x as the square root of x, and f prime of x is equal to 1 over 2 square root of x. So that means that this whole approximation formula is going to be the square root of 16 plus 1 over 2 times the square root of 16 times 1/2. So now all we have to do is simplify and write the final approximation. So the square root of 16 is 4, plus 1 over 2 times 4 is going to give us 8 times 1/2. So we're going to get that this is going to be 4 plus 1 over 16, which is going to be 16 over 16. I'm sorry. Nope, that's a lie. I'm sorry. It's going to be 64, converting that 4 into a fraction over 16, plus 1 over 16, which if we just add across our fractions, we're going to get 65 over 16. So our final answer that we can write is that the square root of 16.5 is approximately equal to 65 over 16, which you could use your calculator to then convert that into a decimal. And once you do that, you could also use your calculator to actually take the square root of 16.5 and see how close they are. So this would be your final answer to the problem. A fraction is always fine. So that's how you go about using differentials to approximate a function value. Now something else we can use differentials for is to approximate the error of something. So there are 3 different types of error that we can estimate using differentials. The first is called the propagated error, which is just delta y. So the propagated error is just the difference between what you actually measure and the value that you should have actually measured, the true measurement versus the measured measurement. Because sometimes when you're measuring something with a ruler or anything like that, there's always human error that you have to take into account. Your measurements or your devices are only so accurate, so precise, so there always is going to be some sort of error when you measure something by hand, unless you have very, very precise instruments. And then we have what's called the relative error, which the relative error is going to determine, is it a big error or a small error? So what it does is you want to compare your differential. So you're going to compare your dy to y. So a lot of times we figure out relative errors for areas or volumes, so it could be something like your differential of the volume over the actual volume, or your differential of the area over the actual area, anything like that. So you just want to compare the differential value to the actual value and simplify that ratio and get a number out at the end. And then we have your percent error, which is just your relative error written as a percent. So all you do is you take your relative error and multiply it by 100. And so those are your 3 types of errors. So the percent error just tells you by what percent are you making an error by. Pretty easy to figure out. So now let's do an example. So we have this ball bearing that's supposed to be manufactured with a radius of 2 millimeters. So a ball bearing is just a really small metal sphere. And ours is especially small because the radius is only 2 millimeters. But during the manufacturing process, this process is only accurate within 2% of 2 millimeters. So we want to use differentials to estimate the relative and percent error in the volume of the ball bearing. So first we want to figure out how accurate we are. So what is within 2% of 2 millimeters? So we want to find 2% of 2 millimeters first. So to do that, we change the 2% into a decimal and then multiply it by 2. So when we do that, we get 0.04 millimeters. But the thing about error is it says within. So that means that we can be within plus or minus 0.04 millimeters of 2 millimeters. So you could be a little smaller or a little bigger. So the plus and minus signs, those are really important to take into account because you can either be bigger or smaller, which is going to give you the plus or minus on your delta. So now what we need to do is we need to set up first the equation for our volume because we're talking about the error of the volume. So the volume of a sphere is just 4/3 pi r cubed. So then we know that our second step is to find our dv. So the first thing we're going to do is just to find our derivative of the volume with respect to r. So when we do that, we're going to get 4 pi r squared, which means that if we just move that dr over, our dv is just 4 pi r squared times dr. So when we're going to take the relative error now, our relative error is just going to be delta v over v. So we know that delta v then was 4 pi r squared dr, and our volume was 4/3 pi r cubed. So our pi's are going to cancel. Both the r squares in the top are going to cancel and leave one r in the bottom. And then if we do 4 divided by 4/3, that's just going to be equal to 3 dr all over r. Now, dr is when the change of the radius is becoming infinitesimally small. So we don't actually know dr, but we can tell you what delta r is. So this is approximately 3 delta r over r. And you might be saying to yourself, well, what's a delta r? This plus and minus 0.04 is delta r because that's how far the change in the radius can be based off of the manufacturing process information. And we know that the radius is supposed to be 2 millimeters. So now all we have to do is plug in for our values. So now we're going to have 3 times plus and minus 0.04 all over 2 millimeters. And then we have millimeters up top as well, which is good because we want all of our units to cancel because we're just talking about error here. So when we do that, when we do 3 times 0.04 and then divide by 2, what we're going to find is that our error is approximately plus and minus 0.06. So overall, it's a pretty small relative error in the manufacturing process because it's such a small number. If we had plus and minus 0.6 or plus and minus even 1, 2, or 6, that's a pretty large error. And now all we have to do is find our percent error, which all we do then is we're going to take this 0.06 and multiply it by 100, which is just 6%. And we can drop the plus and minus sign then because percentages are always positive. So this plus and minus 0.06 is going to be your relative error, and the 6% is your percent error. So there you go. That's how you go about using differentials to approximate error of a measuring process of some sort. So thank you so much for watching. I hope this helped. Have a great rest of your day.